All right, let's dive into current electricity. We're going to break down the 7 most essential derivations you absolutely need for your CBSE exams. We're talking step-by-step guides, the common traps people fall into, and those little tips to help you squeeze out every single mark. Let's get to it.
80%. Just look at that number for a second. What if I told you that by really truly mastering just a handful of derivations and knowing how to avoid a few classic mistakes, you could lock down over 80% of the marks in this chapter?
So, how is that even possible? Well, it's not magic, it's about strategy. A few core derivations are like the foundation of a building for this entire chapter. Once you master them, you start to see how everything else just clicks into place. This whole session is about building that solid, unshakable foundation.
So, I want you to think of this as our blueprint for a strategic heist. We're not just studying randomly, we're on a mission. We're going to target the highest value concepts and presentation tricks that get you the most marks on that exam paper. It's all about studying smarter.
Okay, let's start with our first 3 main targets. I call these the high-yield trio because they pop up all the time as big, multi-mark questions and are, frankly, fundamental to everything else.
First up, we're connecting current with something called drift velocity. That's just the average speed of electrons as they kind of shuffle their way through a wire. The key idea here is super simple. Current is just the total amount of charge that zips past a certain point every single second. That's it.
And the derivation? It's a really logical flow. First, we just write down the basic definition of current. I is charge, Q, over time. T. Easy. For step 2, we figure out what Q is. Well, it's the number of electrons in a chunk of wire times the charge of each electron. The number of electrons is just the number density, N, times the volume of that chunk, which is its area, A, times the distance they travel, VD, times T. Then in step 3, we just plug that big expression for Q back into our first equation. You'll see the T on the top and bottom cancels out perfectly, leaving us with our final formula.
Okay, now listen up, because this is the #1 trap. So many people forget the A for area. Always remember, a thicker wire has a bigger cross-section. It's like a wider highway. It can carry more traffic, or in our case, more electrons. The current absolutely depends on that area. Don't throw away easy marks on this one.
And here's a little insider tip for you. Let's say you panic in the exam and your mind goes blank. If you just write down the expression for the total charge, Q, you're showing the examiner, hey, I get the physics behind this. That alone can rescue you with some partial credit. So the lesson is, always show what you know. All right, our second target is resistivity. Now this one, I think, is really beautiful. It's the formula that connects the tiny, chaotic, microscopic world of electrons bumping into each other inside a wire to a big, macroscopic property we can actually measure, a material's built-in resistance to current.
Let's walk through the steps. It all starts with that expression for drift velocity, V sub d, which includes tau, that's the average time between electron collisions. We then plug that into the formula for current density, J, which is just current per unit area. And for the final move, we bring in the microscopic version of Ohm's law. From there, it's just a little bit of rearranging to get our final expression for resistivity, ρ, which is just the inverse of conductivity.
You would not believe how many people mix up N and tau when they're under pressure. I get it, they can look similar. So here's a simple way to remember. N is for the number of electrons. Think, how many? Tau, on the other hand, is for the relaxation time. Think, how long? Burn that into your memory. It will save you.
Our third big target, the balanced Wheatstone bridge. The whole magic trick of this circuit rests on one super elegant idea. When the bridge is balanced, the voltage at 2 specific points is exactly the same. And if there's no potential difference, well, no current is going to flow through that middle path.
So the derivation literally kicks off by stating that one key condition. The current in the galvanometer, Ig, is 0. Done. That's our starting pistol. From there, we can use Kirchhoff's voltage law on the top and bottom loops of the circuit, which gives us 2 nice, simple equations. The final step? You just divide one equation by the other, and like magic, the famous Wheatstone bridge ratio appears.
And here we go. This is the mistake that I swear everyone makes at least once. They pair up the wrong resistors in the final ratio. Just remember, it's always the adjacent arms in each branch. It's P over Q equals R over S. Drill that into your muscle memory before you walk into the exam hall.
Okay, with the big 3 under our belt, it's time to secure the perimeter. We're going to run through 4 other essential formulas. Think of these as the fundamental tools that you'll need to solve pretty much any other problem in this chapter. First, resistance itself. It just makes sense, right? A longer wire means more resistance, and a thicker wire means less, so R equals rho L over A. Second, equivalent resistance. In series, the voltages add, so the resistances just add up. In parallel, the current splits and then recombines, so the reciprocals of the resistances add up. Third, terminal voltage. This is just a simple energy balance. The total EMF of the cell equals the voltage you get out, V, plus the little bit of voltage lost inside, IR. And finally, the power relations. Just start with P equals V times I. Then, by subbing in Ohm's law in its two different forms, you can easily get the other two versions.
All right, knowing what to derive is one thing. Now we got to talk about how to present it. This is where we get a little sneaky. Let's get inside the examiner's head and figure out how to write our answers in a way that just makes them want to give us full marks.
So what makes an examiner sigh? These are the top 3 unforced errors. Number 1, unit slips. Forgetting to write ohms or amperes is like writing a number without a currency sign. It's meaningless and an easy way to lose half a mark. Number 2, formula mix-ups, like using the series formula for parallel resistors. And number 3, sign errors, especially when you're using Kirchhoff's laws.
The key to avoiding these so-called silly mistakes is to build rock-solid habits now during your revision. So here's your checklist. Always write the formula before you plug in numbers. Always convert everything to standard SI units. Always double-check the axes on a graph. And be obsessive about using your sign conventions correctly. These little things are what separate a 90 from a 98.
Now, if you only take away one thing from this whole section, let it be this. This is pure gold. Examiners literally award marks just for writing down the correct formula. If you jump straight to the numbers and make a calculation error, you could get a 0. But if you write the formula down first, you've already banked some partial credit. It's the safest bet you can make.
Okay, we've gathered our intel. We've learned the insider secrets. Now, let's put it all together into our final getaway plan. This is your complete blueprint for exam day.
And here it is, your exam blueprint. This table is your ultimate guide. It lays out all 7 derivations, how often they've shown up in recent years, how many marks they're usually worth, and what priority you should give them in your final revision. Use this to study smart and focus your energy where it counts the most.
So that's it. The blueprint is in your hands now. You know the 7 derivations that will get you the biggest bang for your buck. You know the common traps to sidestep for each one, and you've got the secrets from inside the examiner's mind. You are prepared for this.
So I'll leave you with this one question. Be honest with yourself. After seeing all these common pitfalls, forgetting the A, mixing up the Wheatstone ratio, messing up signs, which one is your potential weak spot? Which one are you going to make a promise to yourself to double-check every single time? Naming it is the first step to conquering it. Good luck!